Now this one, it's a little more complicated, but it's not too bad. We look at it and say, well, what do I expect? Now one of the things you could try first is your test for divergence. Take the limit as n goes to infinity of your a sub n's. So L'Hopital's derivative of the top, which is 1 over n. Derivative of the bottom is 3n squared. We think of that as over 1. So you flip and multiply. And you get an answer of 0. So the test for divergence, our conclusion is that it may or may not converge. And that's all we know. And so we're like, okay, doesn't save me any time, but we tried it. And then we look and say, okay, what could I use? I could look at all the other tests we know up to now. We know geometric. That's not geometric. It's not a number to a power n. It's not telescoping. That won't work. You could look at this and say, I could do the integral test. I don't feel like integrating. You could try strict comparison, but that's going to take a little bit of work. But then you look and say, okay, well, what else do I know? Well, let's try the limit comparison test with a summation of, we'll try 1 over n cubed. This one here converges. It's a p-series. P equals 3. So we try it with this p-series and see what happens. So put the one you're testing on top. This is very important for this problem. The one you're testing is on top. The one we're testing with is on bottom. Flip and multiply. That's natural log of n. And that gets me infinity. And so when I start seeing the cases, the answers of infinity and 0, provided I did it in the correct order. The one testing has to be on top. The one that we're testing with, the one that we know is on bottom. Then I can come back to my limit comparison test and says, oh, I got an infinity. Is that one of our two special cases? So it's that second one. If the limit's infinity and the one we're testing with diverges, then we get diverges. So I come back here and say, okay, I got infinity. The one I tested with converged. And we are sad to say no conclusion. So that didn't work. At this point, you're like, well, let's try something else. And so I look and say, well, what else could I use? Let's try the limit comparison test with the summation of 1 over n. We know this series diverges. This is our p-series. P is equal to 1. So we have natural log of n over n cubed divided by 1 over n. We flip and multiply. And so our limit becomes natural log of n over n squared. This is a L'Hopital's. So now we take the derivative of the top, which is 1 over n. The derivative of the bottom is 2n. And we do the same work we did up above with our test for divergence. Think about this as over 1, flip and multiply. And we see we get an answer of 0. So once we decide our test, all this boils down to is, can we take a limit? So we go through the work, we get our limit being 0. It's like, okay, this is one of our special cases. We come back to our limit comparison test and say, okay, what was that special case again? If the limit is 0, if the series that we're testing with converges, we got a conclusion. Unfortunately, the one we tested with was diverging. So once again, no conclusion. And at this point, you might be saying, well, let's try a different test. But let's think about this. If I can get a limit being 0, then if the series I test with converged, I'd have something that worked. So up here, when I did 1 over n cubed, notice they all canceled out and left me with just natural log of n. If I did natural log of n over n cubed, when I did that limit, notice that limit became a 0 because of the algebra. The 1 over n, the derivative with the n's in the bottom, I got that value here. When I did it with 1 over n, I still had natural log of n over n squared. So as long as I can keep an n in the denominator, when I do L'Hopital's, I'm still going to get something that's going to go to 0. So if you start looking at the algebra that you did and you say, okay, well, you know, we were fairly close a while ago. Limit comparison test with 1 over n squared. We know this is a p-series. P is equal to 2. We get it converges. And so now you come to the limit comparison test just as before. The limit as n goes to infinity, natural log of n over n cubed, 1 over n squared. When you flip and multiply, you get natural log of n over n. Now at this stage you look and say, okay, now I need to do L'Hopital's. Derivative of the top is 1 over n, the derivative of the bottom is 1, and we see that this limit is 0. So by looking at the previous work for those previous limits, as long as we could compare with something that converges and leaves an n in the denominator, when I take this L'Hopital derivative, I'm going to end up with 0 here. So my limit comparison test, well, says if your limit's 0 and the one you're testing with converges, then your series converges. And so at this stage, our limit comparison test, the series will converge. Now, the limit comparison test that I showed you in this section is different from the one in the textbook. Actually, this test came out of the textbook that I used as an undergrad. So it's a little more powerful in that sense that it has these other two conditions. The one in the textbook says only if L is greater than 0, and then says if L is equal 0 or infinity, you must do other techniques. So that's why I like this one here. But if you didn't do it with this limit comparison test, and this, the one I give you in this section, you'd really have to find a comparison test or the integral test to make this work. So it's not as trivial. Now, our next question, lots of students will look at this and they just sort of freak out. They're like, this is just evil. It's nasty. But in reality, your inner child should be doing backflips. This one is nice. You look and say, okay, what does this look like? Well, it looks like a big mess. But the big thing I notice is in this denominator, it's a product of two things. Remember, we're going to take this fraction and divide by another fraction. So when I flip and multiply, if I choose correctly, I'll choose something that will cancel. So I look and say, let's do the limit comparison test with the summation 1 over 2 to the n. We know this is geometric. We know r is equal to 1/2. So we get converging. And so we look and say, okay, the limit as n goes to infinity. So 3n squared plus 5n over 2 to the n squared plus 1. And here's the kicker. We're dividing by 1 over 2 to the n. So when I flip and multiply, I see the 2 to the power n will cancel out on both terms. And so this becomes a limit as n goes to infinity, 3n squared plus 5n over n squared plus 1. And we look at this and say, hey, take L'Hopital's twice, or look at the highest power of n, that's n squared. We see that limit is equal to 3. So limit comparisons test says both do the same. Thus our series will converge because we were testing with a geometric series that converged. Now our last one here just gets to be a little bit of fun. We have 5 plus cosine of n over the square root of n plus n minus 1. So we look at this and say, you know, it looks fairly similar to a 1 over square root of n. So we're got the idea that this is going to diverge. So that's our whole goal. But that cosine in here makes life a little messy. So I look and say, well, 5 plus cosine of n. Well, I know that's smaller than or equal to 6, and I know that's bigger than or equal to 4. Remember, we're building off of the cosine of n is between 1 and minus 1. So if I add 5 to everything, I get that blue inequality. Or in other words, I get 4 over the square root of n minus 1 is less than 5 plus cosine of n over the square root of n minus 1. And should say less than or equal to 6 over the square root of n minus 1. So the series I want is now between two other series. And we can see as n goes from 2 to infinity, both other series are positive. So on that interval, we see this is positive. And this one here is also positive. So here's the catch. If the bigger fraction, if that series that's represented by that fraction, if that converges, we got converges. If the smaller one diverges, then we have diverges. So all I need to do is figure out one of those two things. And since this is a square root of n minus 1, you know, let's examine the smaller one. We're going to use the limit comparison test with the summation of, we'll just do 1 over the square root of n. Because it's really what this looks like. The 4 is inconsequential. The 4 doesn't change the convergence. The 4 just is a bigger number on top. We could factor the 4 out if we wanted to. The minus 1 on the bottom, as n gets really, really large, it really doesn't come into play. So it looks like 1 over root n. We know this is a p-series. P is equal to 1/2. We know this diverges. So we're testing it with something that diverges. So the limit as n goes to infinity. 4 over the square root of n minus 1 over 1 over root n. Flip and multiply. Now at this stage, most students tend to cringe because they look at this and say, this is going to be a nasty limit. But at this point, guys, this one's really not bad. If you look at it the right way, we can look at this as 4, the square root of n over n minus 1. So we look at it in that fashion. We see that this is the fraction we want to look at. Well, as n goes to infinity, that fraction I boxed in green goes to 1. So this ends up being 4 times the square root of 1, or in other words, 4. So, thus, by the limit comparison test, our series 4 over the square root of n minus 1 will diverge. We did a limit comparison test with a series that diverged. So we got an answer of 4. They both do the same thing. By the comparison test, the series J. Now, I don't feel like writing that whole series down, so let's come back up to the top and we'll give it a name and call it J. That series, 5 plus cosine of n over the square root of n minus 1. Will also diverge. The smaller one diverges, which means the larger one diverges.